All right, in this section, we're going to compare exponential and linear functions. So if you recall with a linear function has a constant rate of change, right? That's the slope of the function is it's constant. That's what makes it a line when you graph it, is that the rate of change is constant. So if you look at, in this case, in this sort of lead-in discussion, we're talking about a population of fish over a 5-year period. And so if initially there's 1,000 fish, you can look at this table and tell that it's linear because the population of fish goes up by 100 fish every year, right? So this is adding 100 fish every year, right? You go from year 0 to 1, you add 100, you add 100, you add 100 every year, and so on. Okay, so you can see that the population of the fish increases by 100 every year. So it has a constant rate of change. Now, in this next table, we have a population of fish that's growing exponentially. And with exponential growth, you have a constant relative rate of change. So if you look at the increase in fish every year, you can see that it's not constant, right? The average rate of change over an interval is not constant. So here it's going up by 100. Here it went up by 110, right? And so on, right? It's not going up at a constant rate. But if you take the ratio of consecutive values, you're always going to get a growth factor of 1.1, right? So if we take 1,000 times 1.1, we get 1,100, and then take it times 1.1 again, you get 1,200, 1,210, and so on. So if you look at the relative rate of change of this second population, the relative rate of change is constant. It's the growth rate is 10% per year. All right. So from a table, we can distinguish between a linear and an exponential function by looking at the difference or the ratio of consecutive y values. Now, I want to emphasize, though, that this only works if the delta x is constant. All right? Only if the delta x is constant. Now, for linear functions, you can, even if the delta x is not constant, you can look at the average rate of change and it should be the same, even if the delta x is constant, because you're dividing by the delta x when you calculate the average rate of change. But for an exponential function, to see that you have that the ratio between consecutive terms is constant, you have to have a constant delta x. All right, so let's take a look at example 1. We're given a table of values and we're asked to figure out which one of these is linear and which one is exponential. All right, now you can have functions that are neither one. So we need to check here. We need to check what's going on. Now remember, if it's linear, it has a constant average rate of change or constant rate of change. All right, now the first thing I want to do, though, is check that we want to check that delta x is constant. All right, and you can see that it is. Right here, the delta x is 3, and then it's going up by 3, and it's going up by 3, and so on, right? It's going up by 3 each time. So we do have a constant delta x, right? If we take the difference between consecutive x values, it's just 3. So we do have a constant delta x. So we can use the what we just learned, which maybe I should scroll up just a hair so you can see what it says. Oops. Maybe not that far. There we go. All right. So you can see what it says. If we have a constant difference between consecutive terms, then it's linear. So let's look at the difference between consecutive terms here. So for f of x, it looks like 3.2 to 4.8. That's an increase of 0.8, right? And this is also an increase of 0.8 and 0.8 and 0.8. So if you take the difference between any of these consecutive values, then you get 0.8. 0.8. So it looks like this one is linear. Okay. Now, if we do the same thing for this one, I think they could both be linear. I might be throwing you a curveball, right? So here we get an increase of 0.8. Here we get an increase of 1. Here we have an increase of, it looks like 1.25. Here we have an increase of 1.56. All right. So you might be tempted to say, okay, that must be exponential, but not necessarily. Not necessarily. We need to check the ratio. So let's look at the ratio. We're told up here that if the ratio between consecutive y values is constant, then it's exponential. So we need to check it. Whoops, ratio, not ration. All right, let's look at the ratios. So if I take 4 divided by 3.2, right? 4 divided by 3.2 is 1.25. 5 divided by 4 is 1.25. All right. 6.25 divided by 5 is 1.25. All right, so you can see here, we look at those ratios between consecutive y values, then we have a constant ratio. So we can conclude that f of x is linear and g of x is exponential. All right, and the reason f of x is linear is because it has a constant rate of change, or it's got a constant difference between consecutive terms. All right, so f of x is linear, and g of x has a constant ratio, so it's exponential. All right, I will meet you in the next video.